Hardly anybody showed up. Maybe more people because the choir concert. How many people are in choir? Oh, good. I get to listen to you guys on Monday. Okay. Will it be a good concert? Hopefully. Okay. See, again, another thing I can't do, sing. Alrighty. So, Caitlin, we're going to start with you. Just as a little review, we have a function inside the function, correct? We take the derivative of the outside function, leaving the inner untouched, and then multiply by the derivative of the inner. That's kind of it, right, in a nutshell. So we've got this first one right here. Do you see it?
Yeah.
And so h prime is going to be, of x, is going to be what?
Is going to be 6x.
Oh, you're going way too fast. Slow down for the old guy, okay? So we got these parentheses, correct? What's the number that's going to be in front?
6x. This is just going to be, oh no, sorry, 3.
3, okay. And then we got 3x squared in here plus 2x.
Yeah.
Raised to what power?
The second.
Second. Now we're going to come in here,
Now,
right?
Yeah.
And I'm going to have parentheses because I'm going to have two derivatives, right, that I'm adding together.
Yeah.
Okay. And I'm going to take the derivative of what's in here. What's that?
6x plus 2.
Plus 2. Now, Caitlin, the good news is you can just leave it like that. It is not helpful to multiply it out, because we're going to want it factored, because we're going to be eventually down the road, we're going to be making these factors equal to 0, because they're going to help us identify those turning around points, because that's where horizontal tangents indicate that the graph or what something's happening in this changing direction. Okay? All right. Denise, you're up next. I'm going to give you a little help. You notice here I got radicals, don't I? So I'm going to write this expression that's in parentheses to a power. And I'm going to call it h of x. And I'm going to write x cubed plus 3, and I'm going to put parentheses around it. And it's going to be a fraction, simply because I have a radical. Do you know what the fraction is? Yeah, the 4 and the 5 are going to be part of the exponent, and they're going to be in fractional form. What goes on top? What goes on the bottom? Yep, 4/5. Okay? And so Caitlin kind of pointed the way which way we're going to go. So what's the number that's going to be out front here?
4.
What?
4/5.
4/5. And then I got x cubed plus 3 to what power now? -1/5. Awesome, you're doing great. Times, we got to multiply by that chain or link.
2x.
Come in here. Take the derivative of this right in here.
I wrote the wrong thing. So
Yep.
it would be 2x to the second. Or 3x to the second.
3x to the second. And the 3 dies, right?
Yeah.
So your final answer is going to be this. You're going to have 12x squared on top, because 4 times 3x squared is 12x squared. And down here, you're going to have your radical, because it's a negative exponent, to the 5th of x cubed plus 3. Yes, sir.
Can we just leave it as 4 or 5 times x cubed plus 3 times, so do we have to write it out like that?
Like this? Yes. And here, that's a great question, okay? And here's the reason why. This is the derivative. Would you agree? The derivative helps us decide where those turning around points are. I'm going to end up calling them extrema, relative minimums and relative maximums. You may have studied that last year, okay? they're also called vertexes if you take a look at in the parabola, okay? To have this in the denominator, if this was equal 0, like if I can solve this and figure out what x is that makes this denominator equal to 0, it could be a turning around point that looks like this. That's a turning around point, correct? But it's a sharp point, isn't it? And this is a turnaround point too. It's a smooth point. All smooth turning around points come from the numerator, and all sharp turning around points come from the denominator. And so we need to know what expression is in the denominator to find it. Does that make sense? So we're not going to do it now, and I'm going to repeat this several times, but we're going to make that equal to 0. And since these are odd powers, we know there's one that exists. So that's a really good question, and that's why we have to do it. And I'm really trying not to have, like up here, it's really a waste of time to multiply it out. Because I want to make that equal to 0, and I can see that -3 makes that equal 0, correct? And I want to make that equal to 0, and I can see that 0 is one of those numbers that make that equal to 0, correct? And so when it's in this form, I can solve it a lot easier. But when I have negative exponents, they got to indicate they got to go to the bottom. Okay. Now, this looks like you want to do the quotient rule, correct? I would suggest don't use the quotient rule. You can, and you'll get the right answer. But here's the problem. It's more work. And here's what else happens, Landry. When you do the quotient rule, you got to take the derivative of 9, right? And that derivative is what? 0. And so it eliminates something, correct? So the reason I don't do it is, one, it takes longer, and I don't know if you've experienced it yet, but time is a quantity that you want to have the most of. So what I do is I rewrite it so it looks like this, because this will be a lot quicker. I'm going to have 9 times the quantity 3x plus 2 to the -3 power. Is everybody okay with that? And now when I take the derivative, and Alexis is going to help me do that, I'm going to take that -3 times that 9 and get what?
-27.
A -27. And I've got 3x plus 2, and this is going to become a -4. And then I'm going to multiply by the derivative, and I'm going to have 3. Isn't that a lot quicker than the quotient rule? And then you're going to rewrite it, and Ty, again, here, this is your question, right? You got a negative exponent. I'm going to want you to write it as a -81 over 3x plus 2 to the 4th power. Because that can be 0. If I have a -2/3, if x is a -2/3, I have 0. So the question is it a sharp point? Is it a sharp point where it turns around? That's what we're going to look at. Okay, and when it's in this form, it's really difficult to see. Okay? You see why that's nicer? Now, anybody in soccer in here? Okay, do you guys know who Alex Martins is? Alex Martins was my student for 3 out of 4 years. Okay, did you know that? Okay, really, he's a math. He might be a physics major at St. Cloud State. He might have graduated by now. I'm not 100% sure. Okay, really good math student. Okay, and so when I showed him, when I did this problem, he got really angry. And he said, "Guess what?" I said, "What?" He says, "You mean you don't even ever need the quotient rule?" I said, "Yeah, you don't ever need the quotient rule." Now, there's sometimes that it's easier to do the quotient rule, but you can get by without using it. It's kind of like duct tape. You can almost fix everything with duct tape. Seriously. Gorilla Glue and duct tape. That's really all you need. You know, if somebody, you know, if somebody's got a wound, you can put Gorilla Glue and wrap it in duct tape and they'll live. Okay? I wouldn't suggest, that's not the best choice, right? But it works. So the product rule is kind of like duct tape. So he got really mad. He says, I'm never going to remember the quotient rule again. I said, well, you can do that. And if you take a look at this, well, we're not yet to it, but you're going to see this in a bit. This isn't what I'm talking about, but I'm going to rewrite it like this. This, you have to use the product rule. But I do write everything with powers, and I put a dot in here to remind me that I got to do the product rule. Okay, because I have two separate things. I have a square root and I have a quadratic, correct? That I'm multiplying. So I'm going to take the derivative and I'm going to ask Allison. We're going to do the product rule. The product rule is right over, I guess Becca didn't raise them up high enough, but you can kind of see it there, Allie. Really, Allie, because it's multiplication and addition, you can take any derivative you want. Which one do you want to do? You want to take the derivative of 3x squared, or you want to take the derivative of this? Right or left? Left. Okay, so what's the derivative of 3x squared?
6x.
So you got to take the derivative of that, and then you can't mess with this one. Okay, you got to leave that one alone. And then you're going to write plus, and then you're going to write the 3x squared. You already did this one, it's here, correct? So now you're going to multiply by the derivative of this one. So tell me what you get. Just look at it like this. What goes in front of those parentheses? 1/2. And then this doesn't get messed with. Now we're going to change that exponent to a what? A negative 1/2. And now we're going to multiply by the derivative of what's in here. 4x. Everybody okay with that? You get to there, you got 7/10 of a point. Now, I hate to tell you this, we got a negative exponent. Okay, and that's my indicator that I got to get a fraction. And so I'm going to write it like this: 6x times the square root of 2x squared minus 1 plus, I'm going to bring out some red pen because this and this can be simplified, right? The 1/2 and the 4, and that's going to be a 2. Now, Allie, I'm going to come back to you in a bit here. So I'm going to have 3 times 2, I got 3x squared times 2x, that gives me 6x cubed. That's in my numerator, correct? Because this has an exponent of 1, this has an exponent of 2, that has an exponent of 1, this has an exponent of 1. They all have positive exponents. This is in my denominator. And this has a denominator of 1, doesn't it? What's the common denominator? You know, I hear it, Allie. Okay. If they would have said it at the same time, it would have sounded like stereo. It was more of an echo-ish type of thing. Okay. Did I ever tell you about my son Sam? Before you were born, because he must have been 2. And he was standing out on our driveway, and he's yelling towards Atkinson's. You know who I'm talking about. And he goes, "Hey! Hey!" I said, "Sam, what's going on?" He says, "Dad, the sky is talking to me." So he heard his echo. He had just discovered an echo. That's the cool thing about being a parent. When your kids learn stuff, it's really cool. And what a poetic thing to say. The sky is talking to me. Okay, I'll never forget that. So anyway, common denominator is square root of 2x squared minus 1. And so I got to multiply this by the square root of 2x squared minus 1. And up here I got to do the same thing. Are you okay with that? So on the bottom, 2x squared minus 1. What happens when I take the square root of 2x squared minus 1 times the square root of 2x squared minus 1? The radicals are gone. So I have this, right? Would you agree with that? So the only thing I would do, Ty, and I know I'm coming back to you, this is what I would want as an answer. 6x times 2x cubed is 12x cubed plus 6x cubed is 18x cubed minus 6x. Because this is easy to make equal to 0 and solve. This is easy to make equal to 0 and solve. And Ty, that is the only reason why. Page 2. Oh, here's the one that made Alex Martins mad, Eden. This one right here. Okay? And I said you can rewrite this one in this form. Which almost looks like the one that Allie did. Except it was positive here, correct? But I'm going to ask Aiden the same questions. We have two derivatives. We're going to have to take each of these derivatives, correct? And they're going to be separated by a plus sign. Are we okay with that? So Aiden, do you want to take the one on the left or you want to take the one on the right? It doesn't matter.
Take the derivative of 7x.
Yeah, that's not a bad choice. That's kind of the way I go, but you don't have to be. But just realize you're going to have to end up taking the derivative over here anyway. So the derivative of 7x is what?
7.
So you got 7 times x squared plus 4 times a negative 1/3. Right? You're just taking the derivative of that. You don't even care about this. Okay? Till now. So I come over to the other side of the plus sign. I'm going to write the 7x. And now you're going to take the derivative of that.
Which is negative 1/3.
Times a negative 1/3 parentheses.
X squared plus 4.
You don't mess around with that. Then what does this become?
Negative 4/3.
Yeah, negative 4/3 times 2x. And Ty, I'm going to give you a warning. I know I've been picking on you, but that's because you can handle me picking on you pretty good, right? You would tell me if to quit, right? Because you asked a really good question, that's why. Okay? This one's going to be icky. Okay, but it's going to be a good one to, I don't know if they've taught you this in pre-calc, but I'm going to see how it goes, all right? So this becomes 7 over the cube root of x, the cube root needs to be a 3 right here. Sorry about that. X squared plus 4. Now, you see this minus sign right here, this negative, everybody? This term is negative, correct? So it's going to be minus, and then it's going to be 14x squared on top. And down here I'm going to have 3, and then I got a cube root again, and then it's x squared plus 4 to the 4th. Like I said, Ty, icky. Ickety, ick, ick, ick. Common denominator. Anybody have a clue? Landry.
Just multiply the denominators together.
Well, yeah, this already has a cube root. You're kind of right. one of the things I got to do is I got to have the 3 over here, correct? So I'm going to multiply by 3. And I'm going to multiply by 3. Okay? The other thing, I already got a cube root here, and I already got a cube root here, correct? But inside here, I only have x squared plus 4 to the first power, and inside here, I got x squared plus 4 to the fourth power. So how do I make this? I got to make this x squared plus 4 to the fourth power, don't I? How do I do that?
X squared plus 4 to the third.
Yeah, I got to multiply by, I think this is what you said, the cube root of x squared plus 4 to the third. I think that's what you said. So I got to multiply, well, so I'm going to get this in my denominator. I'm going to slide it a little bit. Down here I'm going to have this, 3 cube root x squared plus 4 to the fourth power. But, Ryan, that was pretty insightful. I'm going to ask you, see if you got another insightful answer. What is the cube root of x squared plus 4 to the third power? What is the cube root?
It's just x squared plus 4.
It's just x squared plus 4, right? So I'm going to multiply up here by x squared plus 4. That's really all I multiplied by, right? So what I'm going to get here, this is going to be 21x squared. Do you see that? Take away 14x squared. That gives me 7x squared. Plus 21 times 4 is 84. Now, Ty, I'm going to tell you something. Okay? This thing never turns around. This thing is always positive. How do I know that? How do I know I have a derivative that is never negative and never 0? That neither the numerator or the denominator can be 0. Ryan.
Both the x's are squared.
Yeah. What can you square? For this to be 0, doesn't that have to be a negative 84? How are you going to make x squared negative? And I don't let you use I, right? And in here, doesn't this have to be a negative 4 in order for that to be 0? So it's always positive. See how I can save myself a lot of work? I can't see it when it looks like this. But when I get into simplified form, I can look at it, and that process of saying, hey, it's always positive is called analyzation. And I didn't even have to touch my calculator to know that. It's like you're thinking. Okay. I'm going to skip this one and come back to that on Monday. This one we can do, and one of my hints is put these in parentheses. And I think we kind of talked about this yesterday, Elijah. Didn't we do some with trig yesterday? Do you remember yesterday? You don't remember yesterday? Okay. So I'm going to write this as y prime. So you don't have a power to do anything here. You simply have to take the derivative of cosine. What's the derivative of cosine? Negative sine. So I'm going to write negative sine of 3x. 3x. And then you're going to come in here and take the derivative of 3x. And what's that? 3. So that's what it looks like. So your answer is going to be a negative 3 sine of 3x. Are we okay with that? It's different than having the powers because it's a sine function, right? It's a trig function and a linear function. The linear function's inside the trig function, correct? So how do you take the derivative of trig? Well, it's one of these over here that I still haven't written out, have I? I got a lot of work to do. I've been kind of lazy. Okay, Ryan, on this one, I'm going to put parentheses here. I always put them in there. Okay? So that means y prime is equal to what?
Or cosine
Of what?
3x squared.
Yep. Now times what?
6x.
6x. And so my final answer is going to be what?
24x cosine of 3x squared.
Perfect. All right. I think we did this one yesterday. Am I right? Didn't we do this? I always write it like this because that's what it means. It's easier for me to see the derivative if I write it that way. Is it easier for you to see the derivative? It's kind of the opposite of what we just did. So I am going to ask Julia, what is the derivative of this? Yeah, what is it? Well, I got to bring the 2 down in front. And then I'm going to leave the cosine of x alone. I'm going to raise it to the first power. And now I'm going to come in here and get what? Negative sine x. Everybody okay on that? Because the squaring's on the outside. So your final answer is a negative 2 cosine x sine x. Okie dokie or not? All right, I left this one for Owen. Okay, Owen, I'm going to show you something in a little bit, but I'm going to do this. This is how I view this one. I call that nested. There's a function inside a function inside a function. This function is inside the sine function, which is inside this squared function, correct? It looks like this. And for the abysters out there, you won't be able to see this. Oh, maybe you can. Maybe I'll stick this under here. This is called a nested doll. That's Blizzard. Right? Blizzard's like this. And then what's inside Blizzard? Another Blizzard. It looks like this. And what's inside Blizzard? Another Blizzard. And what's inside this Blizzard? Nothing. Okay. So I showed everybody my toys. An Albert Einstein action figure. By Bemidji Beaver bobblehead. But more importantly, my lightsaber. So Owen, let's get back to this. This is the last problem we're going to do today. So f prime of x. What do you think I should do first?
Move the 2 on the thing side.
And leave this baby alone?
Yeah.
And put a 1 up here?
Yeah.
Okay, now what am I going to do? I'm going to put a time sign because I'm going to have some derivatives, right?
Yeah, and then the cosine of 5x to the 3rd power.
God, you're doing awesome. Okay, do I have another derivative?
Do you? That's a good question.
Yes, you do.
I'll pass it on to hydrogen.
You got to take the derivative of that thing.
Okay.
Right? It's another function, correct? It's a cubic.
So 15x squared.
15x squared. And you're done. Well, now we can combine some stuff, right? And you're going to have 30x squared. And you're going to have the sine of 5x cubed. times the cosine of 5x cubed. Looks crooked, sorry. You have to identify I have, in this function, I have a squared function, a sine function, and a cubic function, correct? So I take the derivative of the squared function, I take the derivative of the sine function, and I take the derivative of the 5x cubed function. You do have a problem like that. We're going to skip this. I'm going to come back to that on Monday. All right? Nothing, that's it.